Hi guys, and welcome back to Spaced Out. Today I'll be speaking with an astrophysics researcher who is just entering her junior year of high school. Her name is Christine Yee, and her research interests are compact objects, high-energy phenomena, gravitational waves, and cosmology, and she's currently studying pulsar surveys and glitches. Today we'll be speaking about black holes together, and I'll just be asking her a couple of questions to see where the conversation takes us.
Before we start off with more complicated questions about black holes, I thought we could first define them and learn of how they form. If you'd like to go more in depth about black holes, I have an episode about them that I made previously that you can check out. So Christine, what is a black hole and how does it form?
Black holes are the densest objects in the universe. They're so dense that light can't escape, hence the name black hole. At the center, there is a singularity, which is basically an infinitely dense point where all of the matter is contained. And a black hole's radius is defined by the Schwarzschild radius, which is the closest you can get to the black hole and still be able to escape. That's also known as the event horizon. They form when so much matter accumulates that it can no longer support itself against gravity, in most cases in the last stage of stellar evolution when a star goes supernova.
I'm sure that many of you have known what black holes are, or at least heard of them in the past, so I thought we could just quickly introduce the concept of a white hole, something not commonly talked about. So Christine, could you just explain to us what a white hole is, or just what the idea means?
Yeah, so a white hole is basically a theoretical region in space-time in the universe that looks exactly like a black hole except it behaves the opposite. So nothing can enter, nothing on the outside of it can affect what's inside of the event horizon or the Schwarzschild radius. And instead of sucking matter in, it actually spits out light and energy.
How do they relate to black holes? Like, how are they connected to black holes?
So if you think about it, a lot of scientists think that a white hole is basically a time-reversed mirror image of the black hole. So if you wound a video of a black hole backwards, you would see a white hole. While the black hole event horizon is the point of no return, the white hole event horizon is actually a point of no entry. There are lots of ways to interpret the connection between them. One of them is by solving the complete geometry of Einstein's equations, where you would get a black hole, a white hole, and two separate universes that are connected by a wormhole. That's a really interesting way to think about it, but it does violate our understanding of thermodynamics, and if it exists, it's unlikely to be long-lived. It's probably just another monster in the math where you can solve the equations for it, but you wouldn't find it in the universe. Another interpretation is that when a black hole is close to dying after emitting a bunch of Hawking radiation, it decays to such a tiny size that it can actually spontaneously turn into a white hole and spit back out information and everything it consumed. And finally, the most exciting one, in my opinion, is that a white hole could have actually caused the Big Bang, but this is mostly just theory and we don't have any actual evidence or idea of how they form.
That's super interesting. So, how does a black hole actually affect the space-time continuum? What's its role in that?
Yeah, so black holes can definitely move through space. For example, if it's in an orbit, or if it has some kick velocity from its birth. So Einstein's equations predict a very small frame dragging effect where the space-time metric changes slightly and basically makes space-time kind of drag along with the black hole. So it can make, for example, an orbit precess in the case of rotational frame dragging, which is also known as lens-thirring precession, or linear frame dragging, which is a lot harder to see because we don't have an idea of how black holes would move linearly in a way that we'd be able to see them well. So we can detect this rotational precession really without much difficulty. For example, in the precession of Mercury's orbit around the Sun, or in the recent measurement of the precession of the star S2 around Sagittarius A star, which is the supermassive black hole at the center of the galaxy.
So what do you think would happen if two black holes collided or if they merged together?
Yeah, so that's something we can actually already study with gravitational waves. For example, the Laser Interferometer Gravitational Wave Observatory, or LIGO, and also other missions like LISA and Nanograv. So black holes can form in binaries, or they can end up in them, for example, if two galaxies merge. In the case of supermassive black holes, which form in binaries when two galaxies merge, since there's black holes at the center of every galaxy, they evolve first through interacting with all the stars in the galaxy, which has caused them to fall to the center, and then interactions with stars and gas in the disk around the black holes and then finally by emitting gravitational waves. So those gravitational waves, which are basically ripples in the fabric of space-time, carry away lots of energy, so the orbit gets tighter and they eventually merge together. When they merge, they just form a bigger black hole with the combined mass, and they eventually settle down to the final form and produce gravitational waves both from the final in-spiral and merger, and also a phase called the ring down. The remnant from that merger can be ejected from the galaxy. It's possible, and we probably can't see it very well after it merges unless it interacts with the gas.
And finally, does time move slower the deeper you are in a powerful gravitational field? Meaning that if you're closer to a black hole, could you theoretically be passing through time at a different speed?
Yeah, so that's an effect called gravitational time dilation. The lower you are in that gravitational potential well created by, say, that giant black hole, the slower time passes for you. So that's been demonstrated even with atomic clocks at different altitudes in the Earth's atmosphere, because the closer you are to Earth even, the slower time passes. And it can also be seen through the Shapiro delay, where a pulsar's pulses arrive off time because of time dilation near the sun, which is also a big potential well. Being deep in a potential well also has lots of other effects. For example, photons that are escaping that black hole potential well or any other gravitational potential well experience a similar effect called gravitational redshift, where to escape, they have to lose energy, and that means they get redder.
And that was it with Christine. I hope to talk to her more in the future, and I wish her the best of luck with her research. Thank you for listening.